I discuss the absolute zero reinforced self-play reasoning with zero data paper. I'll be looking at the paper itself today, as well as their blog post, and kind of contrasting the two resources because the paper is quite informative. However, in certain sections, this paper becomes quite mathematically intensive and hard to grasp with many different variables. So I'm only giving a high level overview, and therefore at that point, I'll just switch to the blog post and further discuss information there. In terms of the abstract, we will discuss the highlighted section. So where they talk about a hypothetical future where AI surpasses human intelligence, tasks provided by humans may offer limited learning potential for a super intelligent system. So in essence, they're saying that when superintelligence arrives, that we need to be able to provide them with the means to train themselves. And if they're smarter than us, then our data will be useless to them. And to address these concerns, we propose a new reinforcement learning with verifiable rewards paradigm called Absolute Zero, in which a single model learns to propose tasks that maximize its own learning progress and improves reasoning by solving them without relying on any external data. Under this paradigm, they introduce the Absolute Zero Reasoner, which is like an agent that self-evolves its training curriculum and reasoning ability by using a code executor to validate proposed code reasoning tasks and verify answers, serving as a unified source of verifiable reward to guide open-ended yet grounded learning, despite being trained entirely without external data, which they like to highlight with this really funny graph here. The Absolute Zero Reasoner achieves overall state-of-the-art performance on coding and math reasoning tasks, outperforming existing zero-sitting models that rely on tens of thousands of in-domain human-curated examples. So in this graph, they just say that they have zero data, they have really good performance on math and coding, and that they have beat the previous state-of-the-art models when it comes to really low data reinforcement learning regimes. And just as a kind of prompter, I just wanted to explain reinforcement learning with verifiable rewards with the ChatGPT explanation, since it's a new paradigm. So it's a post-training method that treats an LLM as a policy and fine-tunes it via policy gradient updates using rewards computed by automatic rule-based checks rather than human labels. In RLVR, the model samples candidate responses. Each score is verified, where each score is verifiable by a reward function. For instance, unit tests for code, symbolic check for maths, and the average reward is used to update the policy so that correct reasoning behaviors are enforced. And unlike standard supervised fine-tuning, RLVR can surface latent reasoning strategies learned during pre-training, even when the reward signal is partially or wholly spurious, by treating reward verification as the training signal. So this might give you some intuition. To be honest, even for me, I don't deeply understand RLVR, so I think that's okay. We kind of just want the high-level idea here anyways. And you can get this from this image, which shows supervised learning as saying to the robot, okay, I'm playing to get the flag with this remote, you just do the same thing. Reinforcement learning with verifiable rewards, where you're saying, okay, get the flag. And then in Absolute Zero, it's thinking of how to get the flag, and then it's going to get the flag. And it's funny that they have increasingly better looking robots for each step, which totally is not biased towards their solution. But anyways, this is what this figure description explains. With respect to the introduction, they state that RLVR is kind of the new paradigm used for post-training LLMs. A particular compelling variant is the zero RLVR paradigm used in DeepSeek R1, which forgoes any supervised fine-tuning in the beginning, and it does not use human-generated nor AI-generated reasoning traces and applies RLVR directly on the base model with task rewards. However, these methods still depend heavily on expert-curated distributions of reasoning question-answer pairs, which raises concern about long-term scalability. And another scalability bottleneck has already been identified in the domain of LLM tree training, if you'd like to read this Sutskever OpenAI paper. And then we underscore the need, therefore, for a new paradigm that begins to explore possibilities beyond the constraint of human designed tasks and prepares for a future in which AI will surpass us, which is what they say in the abstract. And in this end, they propose absolute zero, which is a new paradigm for reasoning models in which the model simultaneously learns to define tasks that maximize learnability and to solve them efficiently, enabling self-evolution through self-play without relying on external data. In contrast to prior self-play methods that are limited to narrow domains, fixed functionalities, or learned reward models that are prone to hacking, the absolute zero paradigm is designed to operate in open-ended settings while remaining grounded in a real environment. It relies on feedback from the environment as a verifiable source of reward, mirroring how humans learn and reason through interaction with the world, and helps prevent issues such as hacking with neural reward models. I think they're talking about the reward hacking here. And they use self-play similar to AlphaZero, which was with Go and David Silver. And we believe the absolute zero paradigm represents a promising step. Okay, building on this new reasoning, they also introduced the absolute zero reasoner, which we've already discussed. And it constructs 3 types of coding tasks, which is to infer and reason about one particular element in a program input-output triplet, which corresponds to 3 types of reasoning: induction, abduction, and deduction. And they train the entire system end-to-end with a newly proposed RL advantage estimator tailored to the multitask nature of the proposed approach. 2 observations here that I want to talk about is that code priors amplify reasoning, which is to say that Qwen Coder 7b was able to get to a higher performance than Qwen 7b standard, which is, I guess, implying that code is a compressed and efficient way to essentially convey reasoning capabilities to a model and deduction, etc. And then there's also something where there's a misalignment of the model, which is in the blog post, which I'll show you after we talk about the paper. Here they talk about supervised fine-tuning as a preliminary, which is the minimization of the conditional negative log likelihood between the model's response and what the actual ground truth is. And then they have RLVR, which we have discussed. In summary, both supervised fine-tuning and RLVR rely on human curated datasets of either queries, demonstrations, or verifiers, which ultimately limit scalability. The absolute zero paradigm removes the dependency by allowing the model to generate, solve, and learn from its own interactions with the environment entirely through self-play. So in the absolute zero paradigm, they have a model that can act both as a proposer and a solver. And in this case, pi theta is the language model, which plays the role as a proposer of problems and as a solver. And these are both reinforcement learning policies, which will be fine-tuned, or not fine-tuned, but trained with a reinforcement learning setting or Markov decision process. And before we go to the blog post, let's look at this absolute zero loop, because afterwards it just becomes less appealing as a reader. So it begins with the agent pi proposing task tau. So that is pi propose, which is transformed by f, or I guess right here, which is transformed by f with the environment E into a validated problem with X as the input and Y star, I guess, as the output, and also emits a reward, R propose, for learnability. Then a standard RL step follows where the agent solves X by producing Y, receiving R solve from the environment by matching with Y star, and then the proposer and the solver are jointly trained, and this process is repeated. So this is an overview of absolute zero. Now let's move on to their blog post, which has more, I guess, compressed information that is not that difficult to understand. So they have their abstract here. Let's skip that since we looked at the abstract, and they talk about the zero data. There's a interesting graph here which shows different programs. I guess it doesn't really have a good UI, but there's some programs here that were generated by the model, by the proposer, in fact, in order to train it over time. And then they also show here that it's able to do the spinning hexagon, which is quite difficult for large language models. So this is a summary of what we just talked about. The agent acts in two roles, as a proposer and as a solver, the proposer generating tasks and the solver generating Y, which is the answer to that task. And the environment validates proposed tasks because some proposed tasks might not actually be valid, and also provides the reward such that the solver can access that if it solves the task. We have the same diagram here. And now moving on to the absolute zero reasoner, it is the first implementation of this paradigm, which is using a large language model with the role as both the proposer and the solver in this self-improvement loop. So the absolute zero reasoner employs this unified model, which we've already discussed. And for the proposer, we design a specialized reward function based on Monte Carlo rollouts that encourage the generation of tasks with optimal difficulty, problems where the solver sometimes succeeds and sometimes fails. And this creates the richest learning signal for continuous improvement. So using Monte Carlo rollouts to propose tasks that will be used by the solver to improve its policy. And there are 3 reasoning modes, with each one focusing on either the program, the input, or the output. So for deduction, we predict the output given a program and an input, capturing step-by-step logical reasoning. This tests the model's ability to trace program execution. For abduction, we infer an input given a program and its output, resembling trial and error or search processes. This tests the model's ability to work backward from results. And then induction is synthesizing a program from input-output examples, requiring generalization from partial information, testing the model's ability to discover underlying patterns. And the model begins with minimal seed examples, which is to say that there's some cold start data. So in fact, they do have data. They just kind of set 0 as a way to attract attention, I suppose. But they do have these examples, which according to them are as simple as an identity function, but it is still examples. And this bootstraps it to increasingly complex reasoning capabilities through the self-play and verification. So let's go through the figure for the absolute zero reasoner, where at every iteration, it first proposes a batch of tasks. So where are we here? We propose some tasks conditioned on past self-generated triplets stored in a buffer and a particular task type, either abduction, deduction, or induction. From these generated tasks, Python is used to filter and construct valid code-based reasoning questions. Then a learnability reward R proposed is also calculated for each proposed task. The absolute zero reasoner then solves the batch of reasoning questions, and Python is used again to verify the generated response and compute the accuracy reward R solve. Finally, we update the absolute zero reasoner using TRR++, which must be their trust region policy. I know TRPO is trust region policy optimizer. I'm not sure what TRR++ is. Must be some new reinforcement learning policy method. And yeah, let's just go through it once outside of the text and within the model. We have our proposition. We get our learnability reward from the proposer as well, I guess the environment. And then there's the task types where we essentially just take out one of the 3 triplets. And then we go back to the solver, which will try to reconstruct one of these methods, which will then verify it through Python, and we'll get a reward for the accuracy and a learnability reward from the proposer. And this joint update will improve the policies so that hopefully this cycle can continue. Finally, we do have the absolute zero reasoner algorithm here, which you are welcome to read. I also have a ChatGPT explanation of the algorithm. However, in the sake of time, and since it's only a high-level overview, I will stop the video here. If you have any comments or suggestions, then please leave them in the comment section, and thanks for watching.